Welcome to our channel. Material science chemistry is a fascinating field that explores the connection between the structure and properties of materials. Understanding this relationship allows us to engineer new materials with targeted characteristics like high strength, durability, or electrical conductivity. The image on this slide shows a close-up view of the atomic structure of a crystalline material, with vibrant colors highlighting the arrangement of the atoms. This type of visualization helps us understand how the atomic level structure of a material influences its overall properties and behavior. Exploring these fundamental connections is at the heart of material science chemistry and enables the development of innovative new materials. Atomic structure is the foundation for understanding material properties and behavior. Atoms are composed of protons, neutrons, and electrons. These components dictate an atom's characteristics. Chemical bonds form between atoms due to electrostatic interactions. Understanding ionic, covalent, and metallic bonds is crucial for explaining material properties. Quantum mechanics provides a framework for the behavior of electrons within atoms. It explains the energy levels of electrons and their role in bonding. The periodic table is a valuable tool for understanding the relationship between atomic structure, electron configuration, and chemical properties of elements. Diamonds are known for their exceptional hardness and high refractive index. This is due to the diamond's face-centered cubic lattice structure, with strong covalent bonds between the carbon atoms. Sodium chloride, or table salt, forms a stable cubic crystal structure with alternating sodium and chlorine ions. Graphite has a layered structure, with strong covalent bonds within each layer and weaker van der Waals forces between the layers. Silicon also forms a diamond cubic lattice structure, similar to diamond, which is crucial for semiconductor technology due to its unique electrical properties. Solids can have various types of imperfections or defects in their crystal structure. Point defects are localized issues like vacancies, interstitials, and substitutional atoms. These point defects can influence the material's electrical, thermal, and mechanical properties. Line defects, or dislocations, are linear imperfections that significantly impact strength and ductility. Edge and screw dislocations are two common types of line defects. Surface defects occur at crystal boundaries like grain boundaries, free surfaces, and interfaces. These surface defects affect reactivity and strength of the material. Volume defects are larger 3D imperfections like voids, cracks, and inclusions. These volume defects can significantly impact the overall strength and integrity of the material. Diffusion is the movement of atoms, ions, or molecules from a region of high concentration to low concentration within a material. This atomic movement is driven by thermal energy, which allows atoms to overcome energy barriers and jump to neighboring positions. Diffusion occurs along a concentration gradient, with the rate of diffusion proportional to the steepness of the gradient. Higher temperatures lead to increased atomic mobility and faster diffusion rates, as atoms have more energy to move. There are various types of diffusion, including interstitial diffusion, vacancy diffusion, and surface diffusion. The image on this slide shows a 3D model of a crystal lattice with two types of dislocations highlighted, an edge dislocation and a screw dislocation. An edge dislocation is a linear defect where an extra half-plane of atoms is inserted into the crystal lattice. A screw dislocation is a linear defect where the crystal lattice is twisted around a line, creating a helical ramp. The slide also mentions several strengthening mechanisms that can be used to improve the mechanical properties of materials, including strain hardening, grain size reduction, solid solution strengthening, and precipitation hardening. I'll explain each of these strengthening mechanisms in more detail in the next few slides. Phase diagrams are graphical representations that show the equilibrium relationships between different phases of a material. They depict how the phases change with factors like temperature, pressure, and composition. Understanding phase diagrams is crucial for designing and controlling material properties like strength, ductility, and electrical conductivity. Phase transformations occur when a material changes from one phase to another, like solid to liquid or one solid phase to another. The phase diagram on this slide shows the distinct regions for solid, liquid, and solid solution phases, with sharp boundaries and key transformation points like eutectic and paratectic reactions. Analyzing this detailed binary alloy phase diagram can provide valuable insights into the behavior and processing of these materials. The solidification process involves several key steps that transform a molten material into a solid. First, nucleation occurs. This is the formation of stable nuclei of the solid phase within the liquid. These nuclei then grow into larger crystals, which determines the final microstructure and grain structure of the solid. The rate of nucleation and growth influences the size and distribution of the grains in the final material. Cooling the molten material below its freezing point is crucial for solidification to take place. Understanding these solidification process steps is important for controlling the properties and microstructure of cast or solidified materials. Heat treatment techniques are important for modifying the properties of metals to meet specific requirements. Annealing improves ductility and machinability by altering the metal's microstructure and relieving internal stresses. Quenching rapidly cools metals to increase their hardness and strength, but can also make them brittle. Tempering follows quenching to reduce brittleness and improve toughness and fracture resistance. Case hardening increases the surface hardness of metals while maintaining core toughness, making them more resistant to wear and tear. Ceramic materials are inorganic, non-metallic solids formed by heating and cooling raw materials. They have a wide range of applications, from structural to electrical to optical. There are three main categories of ceramic materials. Traditional ceramics like bricks, tiles, and pottery made from clay, feldspar, and silica. Advanced ceramics with higher performance properties, used in electronics, aerospace, and medical applications. Refractory ceramics designed to withstand high temperatures, used in furnace linings and rocket nozzles. This slide provides an overview of the different types of ceramic materials and their key characteristics and uses. Polymers are made up of long chains of repeating units called monomers. The arrangement of these chains determines the properties of the polymer. Cross-linking between polymer chains adds rigidity and strength, increasing melting point and chemical resistance. Branching introduces side chains, affecting flexibility and density. Polymers can have both crystalline and amorphous regions, which impact strength, stiffness, and melting point. Composite materials combine two or more distinct materials to create a new material with superior properties. By combining materials with contrasting characteristics, composite materials often exhibit enhanced strength, stiffness, and durability. Fiberglass, used in boats and wind turbine blades, is an example of a composite material that combines glass fibers with a resin. Carbon fiber composites, known for their lightweight strength, are used in high-performance vehicles and aircraft. Composites are ubiquitous in our daily lives, and their unique properties make them invaluable in many industries. Corrosion and degradation are critical issues in materials science, leading to material failure and significant economic losses. Corrosion refers specifically to the deterioration of materials due to chemical reactions with the environment. This can affect metals, ceramics, and polymers. Degradation is a broader term that encompasses physical, chemical, and biological processes that weaken or damage materials. Examples of corrosion include rusting, pitting, and crevice corrosion. Examples of degradation include wear, fatigue, creep, and embrittlement. It's important to understand both corrosion and degradation processes in order to develop effective strategies for material selection, design, and protection. Electrical properties are a key consideration when selecting materials for various applications. Conductivity refers to a material's ability to allow the flow of electrical current. Metals are excellent conductors. Insulators hinder current flow, and semiconductors fall in between. Resistivity is a measure of a material's opposition to current flow. Higher resistivity means greater resistance. Dielectric constant quantifies a material's ability to store electrical energy through polarization, important for capacitors and other energy storage applications. Understanding these electrical properties is crucial when designing electrical and electronic systems. Magnetic materials come in different types, each with unique properties. Diamagnetic materials weakly repel magnetic fields due to induced magnetic dipole moments in their atoms. Paramagnetic materials weakly attract magnetic fields because they have unpaired electrons that align with the external field. Ferromagnetic materials exhibit strong attraction to magnetic fields due to aligned electron spins creating a strong magnetic moment. Antiferromagnetic materials have opposing spins in neighboring atoms, canceling out the net magnetic moment, making them weakly or non-magnetic. Optical properties describe how materials interact with light, governing how light is reflected, absorbed, and transmitted. Key properties include refractive index, transparency, reflectivity, and color. Refractive index determines how much light bends when passing through a material. Transparency measures the degree of light transmission through a material. Reflectivity indicates the amount of light reflected from the surface. Color arises from selective absorption of certain wavelengths of light. The image shows a colorful stained glass window, where the different colored glass pieces allow certain wavelengths to transmit through, creating a mesmerizing rainbow effect. Heat capacity is the amount of heat energy a material can absorb or release. This affects how quickly a material heats up or cools down. Thermal conductivity is the rate at which heat energy is transferred through a material. This determines how quickly heat moves through a substance. Thermal expansion is the change in size or volume of a material when its temperature changes. This can cause issues with fit and tolerances in engineering applications. Thermal shock resistance is a material's ability to withstand rapid temperature changes without cracking or breaking. This is important for applications that experience large temperature swings. Nanomaterials are materials with at least one dimension in the nanometer range, typically between 1 and 100 nanometers. Nanotechnology involves the design, synthesis, characterization, and application of these nanomaterials. Nanomaterials have unique properties due to their small size and high surface area to volume ratio. These properties can lead to improved performance in applications like electronics, medicine, energy, and environmental remediation. The image on this slide shows a highly magnified, pristine, uniformly colored carbon nanotube, illuminated by an intense beam of light. This gives a visual representation of the scale and appearance of the nanomaterials we're discussing. Microscopy techniques like SEM and TEM provide high-resolution images of material surfaces and internal structures, revealing details at the nanoscale. Spectroscopic methods analyze the interactions of light with materials to identify their chemical composition, bonding, and structure. Thermal analysis techniques study the thermal behavior of materials, such as melting point, glass transition temperature, and decomposition. Mechanical testing techniques measure the mechanical properties of materials, such as strength, stiffness, and ductility. Sustainability in materials is about reducing environmental impact across the entire product lifecycle, from sourcing raw materials to end-of-life disposal. Key focus areas include resource conservation through recycling, reuse, and waste minimization to support a circular economy. Social responsibility is also critical, ensuring fair labor practices, ethical sourcing, and community engagement throughout the supply chain. Technological advancements are enabling innovations in bio-based materials, recycled content, and closed-loop manufacturing, all of which are crucial for driving sustainability. The image depicts an optimistic, green, and sustainable factory setting, highlighting the importance of these sustainability efforts. The environmental impact of materials is significant, with large amounts of waste, greenhouse gas emissions, water usage, and resource extraction associated with material production and use. Evaluating the environmental impact of materials involves looking at the full life cycle, from resource extraction to manufacturing to disposal. The scale of the problem is staggering: 30 million tons of waste generated globally each year, 20% of greenhouse gases attributed to manufacturing, 10% of global water used for material production, and over 1 billion resources extracted annually. Addressing the environmental impact of materials will require innovations in sustainable material design, production processes, and waste management. As we consider the future, it's critical that we find ways to reduce the environmental toll of the materials that underpin our modern society. The material selection and design process is a crucial step in product development, ensuring the chosen materials meet the required function and operating environment. We start with a needs assessment to identify the key requirements for the material, its intended function, the conditions it will be used in, and any other critical factors. Next, we screen candidate materials based on desired properties like strength, durability, cost, availability, and environmental impact. This helps us narrow down the options. We then thoroughly evaluate the shortlisted materials through lab testing, simulations, and prototyping to confirm their suitability and performance. Once we've identified the optimal material, we refine the design parameters to achieve the best balance of performance and cost-effectiveness. Finally, we evaluate the manufacturing feasibility, considering factors like production cost, lead time, and potential environmental impact. This rigorous process ensures we select the right material and design for the application, delivering a high-performing and cost-effective solution. Failure analysis is crucial for preventing future incidents. We need to understand the root causes of failures to address them effectively. Material characterization is key. Understanding the properties and limitations of materials helps us select the right ones for each application. A thorough design review process can identify potential weaknesses before implementation. This allows us to address issues proactively. Proper safety procedures are essential to minimize the risk of accidents and failures during operation. Following these protocols is critical. Materials processing is the series of steps that transform raw materials into finished products. It starts with acquiring the raw materials, whether extracted from natural sources or synthetically produced. The materials then go through preparation steps like cleaning, crushing, grinding, mixing, and blending to get them into the desired form and composition. Next, shaping and forming processes like casting, forging, rolling, extrusion, and machining are used to create the desired geometries. Heat treatment is then applied to alter the material's microstructure and mechanical properties. Finally, surface finishing steps like painting, coating, polishing, and plating are used to enhance the aesthetics and performance of the final product. The overall process transforms raw inputs into the finished products we use every day. A graphene is a remarkable 2D material with incredible strength, flexibility, and electrical conductivity. It has promising applications in flexible electronics, high-performance composites, and energy storage devices. Enzenes are another family of 2D materials known for their high conductivity, hydrophilicity, and tunable surface properties. Enzenes can be used in energy storage, catalysis, and biomedical devices. Perovskite solar cells offer high efficiency, low cost, and ease of fabrication, making them attractive for renewable energy generation, building integrated photovoltaics and flexible solar cells. 3D printing technologies enable the fabrication of complex, intricate structures from various materials, with applications in personalized medicine, customized prosthetics, and lightweight aerospace components. Biomedical engineering relies on a variety of advanced materials to create innovative solutions for healthcare. Implants and prostheses made from biocompatible materials like titanium and polymers can enhance patient quality of life. Biomaterials play a crucial role in tissue engineering, promoting cell growth and regeneration to repair damaged tissues. Biodegradable polymers and nanoparticles enable the development of controlled-release drug delivery systems, improving efficacy and reducing side effects. Biomaterials are incorporated into diagnostic devices, enabling sensitive and accurate detection of diseases and monitoring of patient health. This slide provides an overview of 4 key energy technologies that are transforming the way we power our world. Solar energy is enabled by silicon-based photovoltaic cells that directly convert sunlight into electricity, powering homes and businesses. Wind energy harnesses the kinetic power of the wind using turbines to generate clean, renewable electricity. Electric vehicles use advanced battery technologies to store energy, reducing our reliance on fossil fuels and lowering emissions. Hydrogen fuel cells offer a zero-emission alternative for transportation, converting hydrogen into electricity. These technologies are made possible through innovations in materials science and engineering, which I'll explore in more depth in the following slides. Transportation relies on a variety of materials to meet key requirements. Lightweight materials like composites and alloys are crucial for fuel efficiency and performance. Durability and resistance to extreme conditions are essential for air and sea travel. The industry is exploring more sustainable material options to reduce emissions and environmental impact. These material innovations are enabling advancements across the transportation sector. Construction materials can be divided into four main categories: structural, finishing, insulation, and roofing. Structural materials like concrete, steel, and timber provide the necessary strength and stability for buildings, bridges, and other structures. Finishing materials like paints, tiles, and flooring enhance the visual appeal and functionality of a building. Insulation materials improve the thermal and acoustic performance of buildings, reducing energy consumption and enhancing comfort. Roofing materials protect structures from the elements and provide weatherproofing, including options like asphalt shingles, metal roofing, and clay tiles. Each of these material categories plays an important role in the construction and performance of buildings and infrastructure. Electronics rely on a variety of specialized materials to function. Semiconductors like silicon and germanium are crucial for transistors and integrated circuits. They enable the miniaturization and high performance of modern electronic devices. Conductors like copper and gold facilitate efficient current flow and signal transmission. Insulators like polymers and ceramics provide electrical isolation, prevent short circuits, and protect components. Optical materials like glass and polymers are used in displays, sensors, and communication networks to transmit and manipulate light. These diverse materials work together to power the advanced electronics we use every day. In conclusion, material science and chemistry are closely intertwined disciplines that drive innovation and technological advancements in various industries. By understanding the fundamentals of materials and their chemical composition, scientists can engineer new materials with tailored properties and applications. The interdisciplinary nature of material science makes it an exciting and ever-evolving field that continues to push the boundaries of what is possible. So, the next time you hold your smartphone, drive a car, or see a new medical device, remember the significant role material science and chemistry play in shaping our world. Thank you for joining us in this exploration of material science and chemistry. If you found this video informative and engaging, be sure to like and subscribe to our channel for more fascinating content.